Okay, a little bit of a different example. Function is a little bit different than some of the ones we've looked at. G of x equals x minus 1 to the 2/3 power. Okay, strange looking function, one you definitely didn't graph in algebra, but again, we can get a lot of good information about the graph using calculus. So in this problem they ask us to figure out where the function is increasing and decreasing, and the intervals where it's increasing and decreasing after we find the critical numbers, and then graph on the graphing calculator. Okay. So, of course, what's the derivative here? Well, okay, this one we can use the generalized power rule on. What we have here is a function raised to a power. So the generalized power rule tells me, perfect, we can find the derivative right away. We take the power down, so 2/3 times the function x minus 1 to the power which is reduced by 1. So 2/3 minus 1 is negative 1/3. Okay? And then we have to multiply by the derivative of the function inside. And the derivative of x minus 1 is just 1. So this is 2/3 times x minus 1 to the negative 1/3 power, or in other words, 2/3 times x minus 1 to the 1/3 power, which finally again we can write as 2/3 times the cube root of x minus 1. Okay, that's our derivative. Now let's talk about critical numbers. Okay, the way we figure out where the function is increasing and decreasing, we find the critical numbers first, because that tells us how to make these intervals, what the intervals are going to be. Okay. Well, remember we have two questions. First we find the derivative, and then we look to see if the derivative is ever 0 or if the derivative is ever undefined. Okay, if those two things ever happen, the derivative is 0 or undefined, those numbers, those values of x, are going to be critical numbers. Okay. So let's look at this one. Is this derivative ever going to be 0? Okay, well, actually, you can say pretty easily it's not, because it's a fraction, and a fraction can only be 0 if the numerator is 0. Okay, so when you have a derivative that's a fraction, you're setting it equal to 0. What you typically do is set the numerator equal to 0. Okay, the only way a fraction can be 0 is if the numerator is 0. Okay, so in this case, we don't have any numbers that make this fraction 0, because 2 can never be made to be equal to 0 by a choice of x. Okay, but the derivative will be undefined. Okay, what does it take to get an undefined result in algebra? Well, the most common one that you'll see is division by 0. Okay, now in the denominator, it's the only place we divide here, right? We do have a cube root, okay, of x minus 1. Okay, now cube roots work for any value of x. You can take a cube root of a positive or a negative number. But there is going to be a problem if we take the cube root of 0, because that's going to make the whole denominator equal to 0. So in this case, probably the easiest way to look at it is, since we have a fraction, we want to really look and see if the denominator is ever 0, because that will make the derivative undefined. So if we set the denominator equal to 0, well, we can cancel the 3. We can divide both sides by 3. We can then cube both sides. Okay, and what we get is x minus 1 is equal to 0. So if x is equal to 1, the denominator is going to be 0, which means the derivative will be undefined. Okay, so we have one critical number here. Okay. X equals 1. Okay, so now we move on into the next step. Okay, we still want this derivative here. Okay, we want to keep the derivative. Okay, but we have one critical number, so we need to start finding the test intervals. Okay, and check and see where the derivative is positive and negative. Okay, well, our critical number was 1. So we're going to have two test intervals, from negative infinity to 1, okay, and then from 1 to infinity. Okay, it's pretty easy to test. Just need to pick a number from each of these intervals, plug it into the derivative, see if the derivative is positive or negative. Okay, so let's look at this. Every number between negative infinity and 1. Well, 0 is in that interval, so what is f prime of 0? Well, it's going to be 2/3 times the cube root of 0 minus 1, which is negative 1. And the cube root of negative 1 is actually negative 1. Okay, so that's going to make this whole fraction negative 2/3. Okay, so on this interval, the function that we're looking at here, the original function, is decreasing. Okay. Now in the next interval, we got to test a point in there too. What number can we test from the interval 1 to infinity? Well, probably 2, right? It's bigger than 1, so that'll work. If we put 2 into this derivative, we'll get 2 over the cube root of, 3 times the cube root. I'm kind of running out of room here. Let me erase a little bit, maybe. Okay, well, I'll erase my work here and do the work up here. What is f prime of 2? Okay, well, it's 2 over 3 times the cube root of 2 minus 1. Well, 2 minus 1 is 1. The cube root of that is also 1. So we get 2/3. So f prime of 2 is 2/3, which is positive. Okay, first the derivative was negative in our first interval. Now it's positive in the second interval. So the function will be increasing on the interval 1 to infinity, decreasing on the interval negative infinity to 1. Okay. Now, in this one, they ask you to graph it, and just to kind of get this one wrapped up here, I'll tell you a little bit about how you graph it on the calculator. Okay. Again, just hit that y equals button on your calculator. Once you turn it on, give you to the equation editor, and just erase everything, anything you might have there from before, and just put in y1. We want to graph this original function, so you can type parenthesis x minus 1 to the power 2/3. And when you type 2/3, make sure you put a parenthesis around the power so it makes that whole thing the power. Okay. And remember, there's this x, t, etc. button on the calculator that will give you the variable x. Okay, now if you go to the top row and hit graph, what you'll see is a good graph of this function. Again, it's going to look something like this, and I'll just draw a portion of it here, okay, based on what I'm seeing on my calculator. Okay, again, strange graph, not one that you're probably familiar with. Looks something like this. Okay. So the graph of this function, g of x, looks like this. Okay, difficult function, one we can't really graph from stuff we learned in algebra, but knowing where the derivative is changing and where it's positive and negative, we can see that this function is correct, and our interpretation from the derivative was correct, that it will be decreasing until x is 1, and then from 1 to infinity, so for x values just past 1, the function will be increasing. Of course, we see that. The function is decreasing up until x is 1, okay, and then for x values past 1, bigger than 1, the function is increasing. Okay.